The simple act of an apple falling from a tree is governed by the very same rules that let us launch massive rockets into space and that keep entire planets locked in their orbits. It's pretty incredible, right? Well, today, we're pulling back the curtain on those rules. Sir Isaac Newton's 3 fundamental laws of motion. These are the elegant principles that, quite literally, dictate how everything in our universe moves. So it really does sound like a riddle, doesn't it? On one hand, you have a rocket launch, this huge symbol of human ingenuity. And on the other, you have an apple. Just falling. What could they possibly share? The answer is everything. They are both playing by the exact same, surprisingly simple set of cosmic rules. And by the end of this, you're going to see exactly how. All right, so here's our game plan. We're going to start with the nature of force itself, the star of the show. Then we'll tackle Newton's 3 laws one by one, the rule of inertia, the famous F equals ma, and the law of action and reaction. And we'll wrap it all up by connecting everything to the one force we all know and feel, gravity. Okay, before we can jump into the laws, we really need to get to know the main character in this whole story, force. Think of it as the invisible push or pull that's responsible for absolutely all motion or any change in motion across the entire universe. So what is a force, really? Well, at its most basic level, it's any interaction that will change an object's motion if nothing else is acting on it. I mean, if something speeds up or slows down or just changes direction, you can bet a force is the culprit. Simple as that. Now, forces basically come in 2 main flavors. First, you've got your contact forces. These are pretty intuitive. Things like the friction that stops a book sliding across a table. They require physical touching. But then you've got the really mysterious ones, non-contact forces, like gravity or magnetism, that can somehow reach out and act across totally empty space. Okay, so now that we know what a force is, let's talk about what happens when there isn't one. And that brings us to Newton's first law. You can think of it as the universe's default setting, or my personal favorite, the law of just keep doing what you're doing. In other words, things are lazy. They're perfectly happy to just stay still if they're already still. And if they're moving, they'll just keep moving in a perfectly straight line at the same speed forever. Nothing ever changes unless some outside force comes along and gives it a push or a pull. And this resistance to change has a name. Inertia. It's an object's built-in reluctance to do something different. And here's the key. The more mass something has, the more inertia it has, right? It's way harder to get a heavy bowling ball moving than a light tennis ball, and it's also way harder to stop it once it's going. That's inertia. So check this out. This classic experiment is the perfect way to see inertia. When you flick that card, you're only putting a force on the card. The coin, because of its inertia, wants to resist change. It wants to stay put. So the card just zips out from underneath it, and gravity takes over, pulling the now stationary coin straight down into the glass. It's brilliant. Okay, so the first law tells us that you need a force to change motion. But the second law, this is where things get really interesting. It tells us exactly how much that motion is going to change. This is where the real predictive power of physics kicks in. Force equals mass times acceleration. F equals ma. I mean, look at it. This incredibly simple little formula is without a doubt one of the most powerful and important equations in all of science. It is the mathematical heart of motion, perfectly connecting the force you apply to something with the change in speed it experiences. Now, these graphs might look a little complicated, but the idea behind them is super simple. The graph on the left just shows that if you have one object, the more force you push it with, the faster it accelerates. Push harder, go faster. Makes sense, right? And the graph on the right shows that if you want to make 2 different objects accelerate at the same rate, you're going to have to push the heavier, more massive one a lot harder. It's literally the physics of why it's easier to push a bicycle than a car. And here is a fantastic real-world example of this law in action. A cricket ball that's flying at you has a ton of momentum. Now, to stop it, you have to bring that momentum to 0. By pulling your hands back as you catch it, you increase the time it takes to stop the ball. And by spreading that stopping force out over a longer period of time, you dramatically reduce the peak force that hits your hands. It turns what would be a painful sting into a smooth, easy catch. It's all about the second law. Which brings us to our third and final law. Now, this one is probably the most famous one of all, but it's also probably the most misunderstood. It tells us a fundamental truth about the universe. Forces never, ever exist alone. They always come in pairs. You've heard that phrase a million times, right? For every action, there's an equal and opposite reaction. But what does it actually mean? Well, it means that if you push on a wall, that wall at that exact same moment is pushing back on you with the exact same amount of force. Forces are always a two-way street.
Okay, and this right here is the absolute key to understanding the third law. The action force and the reaction force are always acting on two times different things. Think about it. If they acted on the same object, they would just cancel each other out and nothing would ever move. This little detail is why anything in the universe moves at all.
Let's just look at the rocket, because it's the perfect example. The rocket's engine exerts a gigantic downward force on the hot exhaust gases. That is the action. And in return, those gases exert an equal and opposite upward force on the rocket. That's the reaction. The forces are identical in strength, but they're acting on different objects. The superlight gas gets blasted away, while the super heavy rocket accelerates up into the sky. And that is how you get to space.
So, to tie all of this together, let's circle back and look at the one force Newton is most famous for. The force that finally answers our very first question, gravity. This was Newton's truly revolutionary idea, the law of universal gravitation. It says that every single object with mass in the entire universe is pulling on every other object with mass. This was absolutely mind-blowing because it meant the same force that makes an apple fall to the ground is the exact same force that keeps the moon orbiting the Earth. It wasn't one set of rules for down here and another for up in the heavens. It was one single law for the entire cosmos.
And this brings us to a super common point of confusion, the difference between mass and weight. It's simple, really. Your mass is the amount of stuff you're made of. It's measured in kilograms, and it never, ever changes, no matter where you go in the universe. Your weight, on the other hand, is just the force of gravity pulling on your mass. So if you went to the moon, your mass would be exactly the same, but your weight would be much less because the moon's gravity is weaker. Here on the surface of our planet, Earth's gravitational force causes things that are dropped to speed up, to accelerate downwards at a rate of about 9.8 meters per second for every second they're falling. We call this special number g, and it's what governs the motion of everything from a single raindrop to, you guessed it, a falling apple. So there you have it. From a simple falling apple to a rocket soaring to the stars, Newton's laws give us this incredibly powerful, unbelievably elegant way to understand motion. For hundreds of years, they formed the very foundation of physics, and they still perfectly describe the world we see all around us. Newton basically solved the puzzle of motion, and it really makes you wonder, doesn't it? What's the next great universal force that we have yet to fully understand?